Thank you all. It's my honor to give you the presentation. I'm Harlu from Peking University. Today, I'm going to talk about first experimental demonstration of self-aligned flip FET, a breakthrough stacked transistor technology with 2.5T design, pure side active, and interconnects. This is the outline of my presentation. Firstly, I will tell you how we came up with this brand new stacked transistor technology. Secondly, the key process steps will be illustrated. Then, I will show you how to design ultra-scaled standard cell and SRAM. Next, the power performance will be compared between our flip FET and other existing advanced logic technology. New concept of interconnects will also be introduced. At last, some other crucial aspects will be mentioned, followed by the conclusions. So, in the first part, I will show you where the inspiration of the flip FET came from. Let's take a look at the history. Back to 2004, our Peking University, together with Hong Kong UST, was the first to propose the 3D stacked transistor, including the stacked planar CMOS and the stacked thin CMOS. The complementary FET, one of the most popular research stacked FET technology, follows the concept of 3D stacked thin CMOS. It has great scalability beyond the gate-all-around FET. However, due to the lack of routing resources, the scaling of CFET standard cell ends at minimum 3 tracks. As we all know, there are two types of CFET. One of them is the monolithic CFET, which is fabricated on only one wafer. It has self-aligned active, but very challenging high aspect ratio process. The other one is the sequential CFET, which is formed by wafer bonding. Fabricated tier by tier, there's no high aspect ratio process in the sequential CFET process flow, but it's difficult to align the top and bottom tiers. So, any third solutions beyond them? In addition to the CFET, functional wafer backside also attracts hot discussions recently. The industry is adapting the SPDN. The backside signal and backside device are now on the roadmap. What's next? We think the ultimate form of functional backside is the backside stacked FET. Then, how to do backside stacked FET? Here comes the solution. The self-aligned flip FET. The self-aligned flip FET takes advantages of self-aligned active from the monolithic CFET, the low aspect ratio process from the sequential CFET, the backside interconnects from the backside signal, and the backside stacked active from the backside stacked FET. As you can see here, it's easy to understand how to build a flip FET standard cell. Just fold a non-stacked FET standard cell. Let the P-FET stack on N-FET, or the N-FET stack on the P-FET in a back-to-back way. And you will get a flip FET standard cell with dual side active and interconnects. Obviously, the standard cell area is halved. As the conventional effective scaling, the pitch scaling becomes slower and slower. The standard cell scaling ends at 6-track 2-fin FinFET. Hyperscaling with DTCO emerges as a key enabler for future logic technology. By DTCO, we can design 1-fin standard cell, such as 4.1T FinFET or 3T 1-fin CFET. What's next? the FET can be the answer. With minimum 2.5 track standard cell design, the FET is a breakthrough technology beyond the CFET. Now, let's talk about how to fabricate the FET. The self-aligned FET process begins with a self-aligned active pattern. Then the frontside active is revealed, and the frontside process is done, just like non-static FET. Here comes the wafer bonding, followed by the wafer flipping. The FET is just named from the flipping process. Next, the substrate is grinded, and the CMP stops on the STI. Back-to-back stacked self-aligned active is then revealed. The rest of the backside process is also done, like standard FinFET or nanosheet FET. Separated flow on both sides, resulting lower aspect ratio processes in the FET than in the monolithic CFET. Note that this picture just represents a schematic process flow. There are some other ways to solve those potential issues, such as the thermal budget. For example, we can flexibly combine wafer bonding and wafer plate flipping to solve these issues. Fabrication of spin-based FET was successfully conducted. This is the SEM image of the FET frontside process. This is the partial backside thinning down. CMP stopping on STI in cross-gate and cross-link directions. Fin profile improvement by novel amorphization process. Fin STI recess to reveal the backside active. Common gate and split gate structure after RMG process. Further treatment can also be used to optimize the backside fin profile, just like this. In this part, I will show you how to design ultra-scaled FET standard cell and SRAM. Let's take the simplest standard cell inverter as an example. In the FET, the InFET is powered by the frontside VSS. The PFET is powered by the backside VDD. Vertical connection is achieved by the drain merge and the gate merge. Especially, in every FET standard cell, the output pin is dual side. This is important for dual side global interconnects, and we will discuss it later. Comparing the FET standard cell with CFET standard cell, we can obviously see that the FET standard cell is smaller. Moreover, the FET has more local routing resources. There are 2 signal tracks and 1 shared power rail on each side. This means 4 signals in total in 2.5T FET, while in 3T CFET with backside power rail, 3 signals in total. So it is easier for FET standard cell design. The question is, are there any other benefits? The answer is yes. The FET separated gate process enables the split gate. The split gate means stacked gates on different sides are controlled by different signals. This is critical for transmission gate and C-squared MOS. For example, in C-squared MOS, some CMOS are controlled by a complementary clock signal. If the split gate is not accessible, some transistors must be cut. This leads to extra area waste. The split gate is very area efficient, especially in sequential logic design, like the D flip-flop. This picture shows D flip-flop of the FET cell design with 7 CPP and 5 tracks cell height. However, the CFET is not split gate friendly. and width area in D flip-flops design because of the larger transmission gate or C-square MOS. Actually, the CFET can support split gate, but extra cell height, like 7T, should be wasted for bottom gate connection to the M0. This picture shows that the 2.5T FET gains extra profits over the 3T CFET with the help of split gate. Yeah, here. Because process on both sides of the wafer are independent in the FET, transistors with dual bipolarity can be supported on one single side. Based on this, we design the bipolar SRAM, compare it with the unipolar SRAM. The unipolar SRAM has simpler process because there's only one transistor type on each side. The bipolar SRAM, though with complex bipolar process, has a smaller bit area and smaller parasitic resistance, but larger parasitic capacitance. Now we come to the power performance analysis. For power performance analysis, we use a 15-stage ring oscillator with funnel 3 and typical back-end-of line load. For fair comparison, we choose FinFET, common gate CFET, and FFET with the same M0 pitch and similar footprint. This picture shows that without back-end-of line load, the FFET outperforms the CFET because of the smaller parasitic RC in the FFET compared to that in the CFET. With back-end-of line load, the FFET also outperforms the FinFET. This derives from the smaller back-end of line load over FinFET due to smaller footprint of the FFET. By modifying some process knobs, such as vertical space or gate height, about 5% frequency gain can be realized in the FFET. With relaxed restriction of space from VS to active, nanosheet in FFET can be much wider than that in CFET. This results in a significant frequency gain at the respective maximum nanosheet width with the same footprint. The nanosheet-based FFET also outperforms the spin-based FFET because of its stronger driving capability. As we mentioned before, the FFET has dual-side global interconnects and a special dual-side output pin in standard cell design. Let's see how it works. For logic gates, the output pin is typically composed of a common drain of a pair of NFET and the PFET. In FFET standard cell, each output pin is linked by the drain merge structure and gets connected to both frontside metal 0 and backside metal 0 to drive the cell at the next stage with input pins on frontside or backside. Dual-side output pin delivers the same output signal and becomes the key dual-side routing enabler. For example, the picture shows an inverter driving the next stage inverter and a NAND. The inverter at stage 2 is driven by the frontside output pin, and the NAND is driven by the backside output pin. The picture on the right demonstrates the 3D schematic of this dual-side global interconnects example. Besides dual-side interconnects, we also have inter-side interconnects, which is enabled by the signal tap cell. Signals can reach the other side through the signal tap cell in non-active region. Note that the signal tap cell is formed by using the same processes as the drain merge. In this way, no extra process is needed for inter-side interconnects, such as the TSV. So here comes the block level evaluation. We do place and route comparison between the common gate and the split gate CFET with BSPDN and FFET with on a RISC-V core. The results show that the FFET has the least design rule violations. That's better routability. The block layouts on the right show that the FFET has huge area reduction compared with the 2 CFET. There are some other crucial aspects. Some of you may have come up with this question. Do the front side and back side transistors have influences on each other? Yes. Electrical coupling is critical. The IDDQ inside the ring oscillator is extracted by TCAP, and we find that it can be reduced by optimizing the well dopants. Furthermore, the coupling leakage can be eliminated by adding an isolation layer on the active, the so-called middle dielectric isolation. Like the monolithic CFET, the FFET can also have both active and gate self-align. This fully aligned FFET can be achieved as shown in the process flow above. The post-epi RMG process brings better thermal budget and variability control. Let's make a summary. The table here shows the benchmark of reported stacked transistor technologies with the FFET. The FFET has self-align active, self-align gate, lower aspect ratio process, higher design flexibility thanks to the split gate, smaller cell size, and better routability thanks to the dual-side global interconnects. In conclusion, the FFET is a breakthrough stacked transistor technology combining the CFET, the backside signal, and backside stack FET. It is somehow a way to achieve the ultimate fully functional wafer backside. With self-aligned active and self-aligned gate, the FFET shows manufacturing-friendly process. Standard cell with minimum 2.5 track design is proposed, with high design flexibility thanks to the split gate. Based on ring oscillator simulation, the FFET has superior PPA over existing advanced logic technology. We propose some new concept of interconnects. First, the FFET standard cell is designed with dual-side local interconnects. Second, dual-side global interconnects enabled by dual-side output pin is proved workable by doing placement and routing. Third, inter-side interconnects is enabled by the signal tap cell. We believe that the FFET is a great candidate for the next generation logic transistors beyond the CFET. Thank you.